Long before oceans carried ships, before forests covered continents, and before the first living cell emerged beneath ancient seas, Earth's surface was already in motion. Hidden beneath every mountain range, beneath every desert, plain, and ocean basin, an immense engine was reshaping the planet. That engine is the lithosphere, the rigid outer shell of the Earth, and its slow, relentless movement has determined the geography of our world for billions of years. Although the ground beneath our feet appears stable, permanence is an illusion. Continents drift, oceans open and disappear. Mountains rise only to be worn away by wind, rain, and ice before new ranges take their place. The landscapes that define the modern world are simply one moment in an ongoing geological story whose timescale stretches far beyond recorded history. The lithosphere consists of Earth's crust and the uppermost portion of the mantle. Together, they form a rigid layer that varies in thickness from roughly 50 kilometers beneath young ocean basins to more than 200 kilometers beneath the oldest continental interiors. Rather than existing as one continuous shell, this outer layer is broken into a series of enormous tectonic plates that slowly move across the softer, more ductile asthenosphere below. These movements are measured not in meters per day, but in centimeters per year, roughly the speed at which human fingernails grow. Yet given millions of years, even the smallest motions become transformative. Continents that were once joined, separate by thousands of kilometers. New ocean floors emerge, while older crust sinks back into Earth's interior. Entire mountain systems rise where plates collide, while great rift valleys mark places where continents are beginning to split apart. The forces responsible originate deep within the planet. Heat remaining from Earth's formation, combined with the decay of radioactive elements inside the mantle, drive slow convection currents beneath the lithosphere. These currents transfer heat outward while exerting forces upon the plates above. Gravity also contributes, particularly where newly formed oceanic crust cools, becomes denser, and begins to sink beneath neighboring plates. This process, known as plate tectonics, represents one of the most significant scientific discoveries of the 20th century. For centuries, coastlines such as those of South America and Africa appeared to fit together like pieces of a puzzle, yet no convincing explanation existed. Only through advances in marine geology, seismology, and satellite measurements did scientists confirm that the continents themselves were moving across the surface of the Earth. The boundaries between tectonic plates are among the most dynamic environments on the planet. Along divergent boundaries, plates move apart, allowing magma to rise and create new crust. Much of this activity occurs beneath the oceans along vast underwater mountain chains known as mid-ocean ridges. Extending for more than 60,000 kilometers, they form the longest continuous mountain system on Earth, though much of it remains hidden beneath the sea. Elsewhere, convergent boundaries bring plates together. Where dense oceanic crust meets another plate, it descends into the mantle through subduction. These immense zones generate deep ocean trenches, chains of volcanoes, and many of the world's most powerful earthquakes. The Pacific Ocean, surrounded by subduction zones, contains the highest concentration of volcanic and seismic activity on Earth, earning the region the name Ring of Fire. Not every collision involves an ocean. When two continents meet, neither easily sinks beneath the other. Instead, the crust crumples, thickens, and rises skyward. The Himalayas continue to grow today because the Indian plate is still pressing into the Eurasian plate, a collision that began roughly 50 million years ago and remains active in the present. A third type of boundary allows plates to slide horizontally past one another. These transform boundaries release accumulated stress through sudden movements that produce earthquakes. The motion often remains invisible for decades before energy stored within the rocks is released in a matter of seconds, reminding us that even seemingly stable landscapes remain part of a dynamic planetary system. Volcanoes provide another visible expression of lithospheric activity. Some emerge directly above subduction zones, while others form where mantle plumes rise from deep within the Earth. The Hawaiian Islands, isolated in the Pacific Ocean, owe their existence to a hotspot that has remained relatively stationary while the Pacific Plate moved across it. Each island marks a different stage in a geological conveyor belt that has operated for tens of millions of years. The lithosphere does far more than create mountains and volcanoes. It influences climate by determining the positions of continents and oceans, which in turn control atmospheric and oceanic circulation. As continents drift toward or away from the poles, global temperatures change. New mountain ranges alter rainfall patterns, while shifting ocean gateways redirect currents capable of reshaping climates across entire hemispheres. Earth's geological history is preserved within the rocks themselves. Layers of sediment record ancient rivers, vanished seas, and long-extinct ecosystems. Igneous rocks preserve evidence of volcanic activity that shaped the early planet, while metamorphic rocks reveal the immense pressures and temperatures experienced deep within the crust. Together, they form an archive spanning more than 4 billion years. The oldest surviving continental rocks, found in regions such as Western Australia, Canada, Greenland, and Southern Africa, originated during Earth's earliest chapters. They formed when the young planet was still cooling, providing rare windows into conditions that existed long before complex life evolved. Throughout deep time, the continents have repeatedly assembled into supercontinents before breaking apart once again. Rodinia existed over 1 billion years ago. Later came Pannotia, followed by Pangaea, which united nearly all of Earth's land around 300 million years ago. As Pangaea fragmented, the Atlantic Ocean gradually opened, and the continents slowly migrated toward their present positions. These immense cycles continue today. Africa moves steadily northward. Australia drifts toward Southeast Asia. The Atlantic Ocean widens while sections of the Pacific slowly contract. Given enough time, today's map of the world will once again become unrecognizable. The lithosphere also provides the foundation upon which human civilization developed. Fertile volcanic soils have supported agriculture for thousands of years. Mountain ranges have shaped trade routes, cultures, and political boundaries. Valuable mineral deposits formed through ancient tectonic processes now supply the metals that underpin modern industry, technology, and infrastructure. Yet the same forces that make Earth habitable also present constant hazards. Earthquakes, volcanic eruptions, landslides, and tsunamis remind us that our cities occupy landscapes still being shaped by geological processes that neither recognize nor pause for human history. Advances in monitoring and geophysics have improved forecasting and hazard assessment, but the underlying mechanisms remain beyond human control. Today, satellites measure tectonic motion with millimeter precision. Networks of seismometers record earthquakes occurring around the globe every day. Deep drilling projects, laboratory experiments, and computer simulations continue to refine our understanding of Earth's interior. Each discovery reveals a planet that is neither static nor finished, but continually evolving. The lithosphere is more than the solid ground beneath our feet. It is the framework upon which oceans formed, mountains rose, climates changed, and life diversified. Every continent, every landscape, and every civilization exists because Earth's outer shell has remained in motion for billions of years. Human history occupies only the thinnest layer of this immense timeline. Beneath every city, every road, and every monument lies a geological foundation forged through processes older than multicellular life itself. The landscapes we inherit are not permanent creations, but temporary expressions of a planet that has never ceased to change, and whose slow movements continue to shape the future long after our own age has passed.